Okay, so this is the fourth day of our unit. We talked about combinations, permutations, counting problems, and we did already did a day on probability. This problem right here, this is the first kind of problem we talk about probability. This is the problem you're going to see in the test. Pretty much the same thing. I think I just, instead of doing like pennies, I think I do balls. So let's just see what we do. Okay. So we got two coins that are selected at random. Now this is different than what we're going to see today because they're taken out all at once. They're taken out in a group. These two coins are taken out at once. Okay. So it says find the probability of each selection. So in number 1 here it says the probability that we put our hand down this bag and we take out two coins, that those two coins are pennies. All right. Well, if I'm taking stuff out in groups, remember when we use combinations. Combinations is groups. Groups is combinations. Okay. So whenever we're doing it, we have to on top remember put all of the ways we can get 2 pennies, all of our successes. On the bottom is every other outcome of getting 2 coins. So you got to think about it. So how can I account for every possible way of taking out groups of 2 pennies? Yes, 3 pennies. I'm choosing 2 of them. Of my 3 pennies, I'm doing all the unique groups of 2 I can take out. That's what that notation means. This does not mean 3 halves. This does not mean 3 divided by 2. This means 3 choose 2. Okay? We'll talk about how to do that again in the calculator here in a second. Remember, it's under math over to PRB, and you're choosing option number 2. 2, I think. All right, so now that's all of the possible ways to get 2 pennies. That's all of my successes. On bottom, what do I put? What was that? No. Is it for combination?
Yeah, combination.
What's 2?
P.
Oh, yeah, okay, sorry. Please, God, yes. Do not do permutations. It's combinations. My bad. Thank you. I changed that pretty good. 2 and 3. But anyway, on bottom is all the possible ways of getting 2 coins. Any 2 coins. That's all of my outcomes. That's 25 coins. Choose 2. Alright. Let's just set them up right now, and then we'll find some answers. I'll let you find some answers to them just for the sake of time. For number 2 here, we got 2 dimes. Okay, so look at your individual thing. We got 4 dimes total. So of those 4 dimes, I'm choosing 2. And then 25 choose 2. It's the same number on bottom. Okay. The denominator is going to be the same because that's just my total number of ways of selecting 2 coins. The denominator will always be 1 combination, and it'll always be your total choose the total number of coins that you're trying to pick. But like for number 3, what's the difference here? Yes. You got 2 separate categories. You got 2 separate parentheses or combinations on top. So like on top, we have 8 nickels. We're choosing 1. We have 4 dimes. Choosing 1. All over my total again, which will always be 1. It'll always be 1 combination. 25. Choose 2. Make sense? Anything else? While I'm taking attendance real fast, at least set these up. At least set up number 4, number 5, and number 6, and then we'll test these in the calculator. Okay. All right. These last 3 are all the same as number 3. All you have to do is just set them up in their individual categories, right? So if I say 1 quarter and 1 penny, well, that's 2 parentheses. And that would be, what, 10 quarters, choose 1, and 3 pennies, choose 1. Is that right? And then divided by, again, the total is still going to be the same, 25, choose 2. Okay. And then number 5, we got 1 quarter and 1 nickel, so separate the 2 categories. All right, so 2 parentheses. Because we multiply separate events there. 1 quarter would be 10, choose 1. 1 nickel would be 8 nickels, choose 1. And then all over 25, choose 2. How many dollars do I have in the problem or in life? Because in life, it's probably about the same amount as this problem. Okay, to be honest, oh God. All right, what about number 6? What would that look like? Nah, yeah, good point. There's this problem like that in your quiz too, and people ask me every year. Yeah, I know it says we're picking 2 coins, but let's assume in this last one that we are picking 2 coins, right? So let's just separate it again in those 2 categories. All right, so for the dimes, we got 4 dimes. I'm taking groups of 2 out, and we got 10 quarters. I'm taking groups of 1 out. The only thing that changes though is your denominator. Instead of 25 choose 2, we're doing 25 choose 3. Okay. Any questions on how we set that up? Let's do it in the calculator real fast. And when we do it in the calculator, people that are watching this video, do what I talked about right here. For the first one, I'm getting 1 over 100 or 0.01. So let's test that ourselves. All right. So we are recording. Okay. So the problem we just did for warm-up, that's our first type of probability. We got really 2 different types of probability problems now that I want to talk about today that I break down into, well, 2 categories each. So really, I guess 4. But they're all boxed. Okay, they're all put in a box. They're all described in there. And there's example problems after each one. The first type I'm going to talk about are then statements. Okay, so the whole front side of your paper are then statements. I break them up into 2 categories: independent events, 2 independent events, and then 2 dependent events. The difference between the 2, and they're really done the same way. Okay. So look at the first one here. It says if 2 events A and B are independent of each other, then the probability of both events occurring is just the probability of A times the probability of B. That's it. All you got to do is multiply. And you'll see independent events with then statements. So look at the wording in these next few problems. You'll always see the word then. Instead of taking stuff out as a group, you're doing one after the other. So something, then something, then something. That just means multiplying. And I think the problems are today are a lot easier than the problems for one. So, and here's an example. It says a die is rolled 3 times. Okay, so I'm not doing it all at once. I'm doing it one after the other. Find the probability of each event happening. A 1 is rolled, then a 2, then a 3. So I want to know the probability of that outcome happening. Right. And they are independent of each other because what I roll the first time does not affect what I roll the second time, right? That's what makes them independent. One does not affect the other. So I got 3 separate probabilities, and they're all independent. You just multiply them. So think about it. Logan just said it. Well, the probability of getting a 1 is 1 out of 6, right? The probability of then rolling a 2. There's only 1 2 on a 6-sided die, so again, that's 1 out of 6. Then the probability of rolling 3, well, that's 1 out of 6. Okay. I need you to be on point with these calculator operations because I don't have them. But I believe, if my memory is right from first class, that's 1 over 216. But if you can give me the decimal, that'd be awesome. 0.004? So yeah, well, 0.04, 0.05% chance. There's a 0.4% chance of this happening. And the farther you go down the line, the lower that probability is going to be because you're really narrowing it down to specifics. Like if I say the probability of rolling a 1, then a 1, then a 1, then a 1, then a 1, it's going to be a very low probability because of all the possible outcomes that you can have. So, make sense? B here, this when you see the word then, okay, it says 2 odd numbers, then a 6. That's saying an odd number, then an odd number, then a 6. So it's still, then statements is still one after the other. So it's still the same wording. Just be careful. It is still 3 separate probabilities. Okay. What's the probability of rolling an odd number on a 6-sided die? 1/2. Or I should say 3 out of 6. Just to show you that, yeah, your options are 1, 3, or 5. What's the probability of rolling another odd number? 1/2 or 3/6, yeah. What's the probability of rolling a 6? 1/6. And again, multiply. Okay. So what's that? 9 over 216. It's a little bit higher of a probability, but not much. Questions on that? That makes sense? Let's do a couple more problems with that. All right, look, okay, so that is. All right, so it says a box contains 5 triangles, 6 circles, and 4 squares. So this problem is starting off very similar to the one from our warm-up. But look at the wording. It says if a figure is removed, replaced, keyword is replaced, and a second figure is picked, what is the probability that a triangle, then a circle? So your then statements means we're multiplying it. It means one after the other. We're not taking them out as a group. It's one after the other. Okay? All right. So we'll start off with the first one. What's the probability of getting a triangle? We got 5 triangles. What's the total number of objects we're picking out of? 15? Yeah, so to get a triangle the first time, what is a 5 out of 15 chance? You got 5 options out of 15 in order to get that. Now, because it says, you're going to see that a lot of problems have the keyword replaced or without replaced. Because it says replaced, it means that they're independent events. Because this probability does not affect my second probability. Because we have an equal chance. Nothing has changed. It's going to be times by, then the probability of getting a circle, we have 6 circles out of 15. So, we've got a decimal for that. Yeah. Good. So you have about a 13.3% chance of doing that. Okay. Any questions on that? Does that make sense? I do want to do this problem just because I do a lot of problems with drawing a card from a deck of cards. So if you don't know anything about a deck of cards, I'll have it posted on the board when you take a test or something. So if you have any questions about it, just ask me. I don't think that would be the reason you get the problem wrong. But it says that you draw a card from a standard deck, replace it, so that means independent, before drawing a second card. Find the probability that the second card is an ace if the first card is a queen. Okay. So we'll start off with that first card being a queen. How many queens are in the deck of cards? 4. How many cards are in a deck of cards? Nice. Okay, cool, yes. So you have 4 queens out of 52. It's being put back, so nothing's changed. What's the probability of getting an ace? How many aces are there? Nice. Okay, 4 out of 52. Good. Decimal. Let's go to decimal. Or you care about fraction. Thank you. So relatively low chance. Relatively low chance. The second card is a heart if the first card is a heart. Okay, so so I've got this deck of cards. I pick a card, it's a heart. I put it back in. I take another out, it's a heart. So let's see. How many hearts are there in a deck of cards? 13. Nice. Yeah. So there's 4 suits in the deck of cards, equal number of each. So 52 divided by 4, 13. So basically it's 13 over 52 times 13 over 52, or 1/4 times 1/4, which is 1 over 16, or something. 0.0625. That's the probability there. All right, questions on independent events. Now, with dependent events, it's the same exact way, same exact thing. You're just going to have to account for the one that depends on the other. So if you notice in the parentheses here, or in the box, for 2 dependent events, it's the same exact definition. You're just going to take the probability of the first event times the probability of the second event following A. So we're going to have to adjust that denominator a little bit. That's what we got here. Look at the example. It says we have 3 quarters, 4 dimes, 7 nickels, and a change purse. Suppose 3 coins are selected without replacement. The key word without replacement means that we have a dependent event, because what happens the first time changes what happens the second time. Does that make sense? Like, it depends on what coin we pick the first time. It changes my probability. What is the probability of selecting a quarter, then a dime, then a nickel? Okay? The then statements mean we multiply. So let's start with a quarter. What's the probability of getting a quarter? 3 out of 14, because you have 3 quarters. There's 14 total. All right, what's the probability of getting a dime then? Yes, we have 4 dimes. I've kept that quarters. I'm not replacing it. I'm not putting it back. So now instead of out of 14 coins, I'm out of 13 coins. That's what it means to be dependent. The denominator changes. Now I got a quarter, now I got a dime, and I'm not putting either one back. So now my denominator goes down to 12. And the probability of getting a nickel, well, I have 7 nickels out of 12. We're going to multiply those. Okay. 0.038. Perfect. So about a 3.8%. Makes sense? Questions on that? All right, how about this next one? A basket contains 4 plums, 6 peaches, 5 oranges. Notice the pattern. It's the same kind of problems every single time. You got to notice keywords, okay? I can say you're taking them out as a group. I can say you're taking them out one after the other with replacement, without replacement. Just notice keywords. What is the probability of picking 2 oranges, then, so then means multiply, a peach if 3 pieces of fruit are selected at random without replacement? So you need to think, oh, without replacement, one depends on the other. Then means I multiply them. So let's have 3 probabilities multiplying by each other. So remember what I said, 2 oranges, then a peach. That means 1 orange, then another orange, then a peach. So what's the probability of getting 1 orange? Yeah. We got 5 oranges out of 15 total fruits. What's the probability of getting another orange then if I hold on to that orange? 4. Yes. We got 4 oranges left to pick from. Ow. Anyway, so I'm all 4 15s, thank you. Because we went down by 1 fruit, it was both in the numerator and the denominator now. Okay. And then I'm keeping both of those, so I'm down to 13. And how many? 6 peaches, thank you. Y'all are getting the hang of this. What's the... Thank you. Wait, 4096? Oh. All right. Questions on then statements? Okay. So we had independent, dependent. That's then statements always multiply. And this problem is very similar. Try it on your own if you want to, but it's on the notes filled out on my website, but I'm not going to do it on the video. All right. Now, or statements. So the first one was then, now we're talking about or, and that's all about adding probabilities. Okay? You don't have to read this right here, but let's look at the example. The events of rolling an odd number or a number greater than 5. So the key word here is or. Or implies that you add. And if you notice, we're only rolling an event, we're only rolling this die once. So it's not something that I'm doing then. It means I'm just rolling it once. It wants to know the probability of different possible outcomes happening in that one roll. So, like, what's the probability of getting an odd number on a 6-sided die? 3 out of 6, right? It can either be 1, 3, or 5. What's the probability of getting a number greater than 5? 1 out of 6. 4 means to add those, so my actual probability is 4 out of 6. Right? Which is like 0.667, sure. I mean, think about why that it means to add. Because if I'm rolling the die once, my options are 1, 2, 3, 4, 5, and 6. It wants to know the probability of it being odd or greater than 5. Well, this is an odd, this is an odd, this is an odd, and this is a number greater than 5. Well, that's a possible 4 options out of 6. That's why we add. We're just adding up all the possibilities. That's what or statements mean. Okay? Does that make sense? See that? Now, again, with or statements, I divide into 2 categories. Instead of independent and dependent, we have mutually exclusive and inclusive. So the first one I want to look at is mutually exclusive. Okay? Mutually exclusive events. Those are 2 events that cannot occur at the same time. Okay? These sets are disjoint, meaning they have no overlap. An example, the probability of drawing a 2 or an ace. Can a 2 be an ace? No. A 2 and an ace are two different things. An example of things that are not mutually exclusive. What about a 9 or a heart? Are those two things mutually exclusive? No, because a 9 could also be a heart. And we'll talk about how to take care of those in a second. Okay? Right now, we're just focusing on mutually exclusive. All you have to do is just add the two probabilities together. If they're mutually exclusive, just add them together. That's it. So look at this example. A bag contains 45 dot eggs. 15 are yellow, 12 are green, and 18 are red. Again, it's the same type of problem, just worded a little bit different. What is the probability of selecting a green or a red egg? Those are mutually exclusive because a green egg could not be a red egg. Right? So we just add those together. What's the probability of being green? 12 out of 45. What's the probability of being a red egg? 18 out of 45. So if I select one egg at random, what's the probability it's green or red? You just add them together. 30 over 45, which I believe is still 0.667. Is that 2/3? Does that make sense? Mutually exclusive or states. Let's look at another example. Keisha has a stack of 8 baseball cards, 5 basketball cards, and 6 soccer cards. And again, same type of problem. She selects a card at random from the stack, just one card. What is the probability that it is a baseball or a soccer card? Okay. Or it means to add. I got 2 separate events here. What's the probability that it's baseball? 8 out of, is that 19 total cards? Yeah. And a baseball card cannot be a soccer card. They're mutually exclusive. So that would be 6 out of 19 for a grand total of 14 out of 19. So if I wanted the probability of getting a baseball or a soccer card, well, I have 14 possible cards I can pick from out of 19, which is 0.7 something. Thank you. Questions on that? All right. Well, so with or statements, we have the mutually exclusive. Let's talk about the other kind, which is inclusive events. Inclusive, and they can be the same. This example says, is the probability of drawing a queen or a diamond from a standard deck of cards, is that mutually exclusive? Go ahead and star this problem, because I basically copy and paste that and put it on the test. So if you just want to star that and say, hey, that's on the test, I asked like 2 questions, I think, with that. Are those mutually exclusive? No. A queen could be a diamond. No. A queen could be a diamond. All right, so if one could be the other, with or statements, we have to adjust them a little bit when we find the probability, and that's what the last box is about. So you have 4 boxes that you should probably keep in mind, that you should study, that you should know. Okay. So the probability of inclusive events. So if two events A and B are inclusive, and the probability of A or B is the probability of both, so add them together. And then all you have to do is subtract the probability of the overlap. That's it. So let's skip down to this example right here. I'll come back to the first one, but let's skip to this example right here just because we've been talking about cards. It says, find the probability of drawing a king or a heart from a standard deck of cards. All right, so or means to add. Okay, so whenever you're doing or questions, you always have to ask yourself, are they mutually exclusive? Is being a king and being a heart mutually exclusive? No, because you can have a king of hearts. What's the probability of getting a king? 4 out of 52. Yeah, there's 4 possible kings out of 52. What's the probability of getting a heart? 13 out of 52. Good. Now, because they're not mutually exclusive, we have to subtract off the probability of both. What's the probability of it being both a king and a heart? 1 out of 52. Okay, 1 out of 52. So add them together, what's that? It's like 16 out of 52. It's like 0.3 something, I think. Point what? 0.307, good. All right. For my visual learners, I think that maybe this will help. Like, here's a standard deck of cards, 52 cards. If I'm talking about the probability of being a heart or a king, like here's all of the options or all the outcomes of being a heart. Okay? And then all of my kings are right here. So if I were to just straight up add both of those together, I'm counting this card in the middle here in the intersection. I'm counting that twice. So what you have to do is subtract it out once. You have to subtract out the overlap. See how that works? Some people just adjust for it already in their head. But what's that? I was about to say, some people just do it in their head, and instead of doing 13, they would do 12. But that's, yeah, you're right. Yeah, if you didn't already notice the overlap, adjust it without, it's fine. So any questions on that? All right, let's do, I think we got like one more example in there. We'll call it. I think, I don't know. All right, let's try this. The enrollment at Southbury High School is 1,400 students. We have 550 students that are taking French. We have 700 that are taking algebra, but there's 400 that are taking both algebra and 550. So there's 400 that are incorporated in those two categories that are also in the other. What is the probability that a student selected at random takes French or algebra? Okay, well, 4 means to add. So we need to find the probability of French. We need to find the probability of algebra. Add those together, but are they mutually exclusive? Well, no, because you could be in both French and algebra. So you have to subtract the overlap. Okay. What's the probability of being in French? 550 out of 1,400. What's the probability of being in algebra? 700 over 1,400. Well, if I do that, I'm counting some of them twice. I got to subtract the overlap. I got to subtract 400 out of 1,400. So, oh, my bad. Thank you. I'm going to believe that's what, 850 over 1,400? Or something. Yeah.
I'm confused because like 550, 700, 400 isn't 1400.
Exactly, because some of them are counted for twice. Like these 400 are a part of the 700 and 550.
Okay, but those two don't equal 1400.
Okay, let's think about it this way then. Let's draw a Venn diagram to model it. Some students don't take either. So here is French, here is algebra. You have 400 here, which means in French you have 150 because that adds up to 550. And then over here you have 400 and 300 will add up to 700. And if you add those numbers up, you end up getting 850. But remember how we talked about our whole universe of students. Okay, there's 850 here. 1,400 minus 850 is 550? Yeah, 550 here. So it's not going to add up to the total. Not every student at the school is taking algebra. We're actually going to have a whole unit on this in our stats. Huh? Okay. Anyway, what's that equal? What's that decimal?
0.687.
Or 60.7%. Yeah. Any questions on that? Done? Ta-da! We're done. So before 11:02, Forbes, let's get it going. Yeah, well, you know. So yeah, we had 4 things. So just know those 4 things. Really 2 things broken into 2 categories. That'll everything up to this point will be on your take-home quiz. I'll pass out tomorrow. Good luck. Oh, 5, 4, 3, 2, 1.